Now that we've seen how submaps can be recombined and reused to form hierarchical representations that are useful for map induction, and that leads to efficient exploration, we ask how humans are able to store the vast amount of spatial information that they experience through their lifetimes. More specifically, we ask, can we build a content-addressable memory with a smooth trade-off between the number of memories and their richness? As we saw before, we know that human-like memory should exhibit a continuum. So given an upper bound on the amount of information that can be stored in any network, which is given by the total number of synapses in the network as shown by previous theoretical work, we want to build an architecture which leads to complete recovery of small number of memory states up to partial recovery of many number of memory states with gradual degradation of information per pattern as we store more patterns into this network. So memories should only be gradually forgotten, and key is to recover all the stored memory states, although with lower information or accuracy per memory. And as we saw before, existing content-addressable memory models lack a memory continuum. They show a memory cliff and only form points on this memory continuum. And what we want is an architecture that can show a smooth trade-off between the number of patterns and the richness of those patterns, spanning this entire continuum. And that's a model that I'll present, which is able to accomplish this continuum. So the model is called MESH, or memory scaffold with heteroassociation. It's a 3-layer recurrently connected network with some weights that are fixed and some weights that are learned through one-shot unsupervised Hebbian learning type learning routes. And so the key behind MESH is that it factorizes the memory or the fixed points from the content that needs to be stored in the network. So the first 2 layers of this network implement a memory scaffold, which you can think of as an underlying attractor manifold with predefined fixed point states embedded into it. The total number of states that can be embedded on the memory scaffold is given by NL choose K, where NL is the dimensionality of the label layer states that are K hot. And this scales exponentially in the number of label neurons. Now, if we want to store content in this network, we can represent arbitrary patterns through the feature layer that is associated to the scaffold through heteroassociation. For instance, if I wanted to remember my dad's favorite shirt, I would just take that memory and tag it onto one of the predefined fixed points. If I wanted to remember someone I met at a conference, I would take that memory and tag it onto another fixed point on the scaffold, and so on and so forth. Now that we've stored content into MESH, we test MESH similar to any content-addressable memory model, where given a noisy or partial input, we want to see whether MESH is able to reconstruct these stored memories. We find that MESH exhibits a near optimal CAM continuum. For patterns up to the dimensionality of the hidden layer, MESH is able to reconstruct complete information for all of those patterns. However, as we store patterns greater than NH, it leads to gradual degradation of information per memory. So again, it leads to complete recovery of all information up to NH memories, partial recovery of each of the memories beyond NH, with gradual degradation of information per memory as we continue to store more memories into this network up to the upper bound of NL choose K. When we compare this network with existing networks, we find that in existing networks, as we increase the information stored per synapse, the information recovered per synapse goes down to 0. Whereas in MESH, given a network of fixed size, the total information is invariant to the number of stored patterns. And this indicates a smooth trade-off between the number of patterns that can be stored in MESH and the richness of those patterns. We also find that in addition to discrete patterns, MESH can also store continuous value patterns with the same gradual degradation. And in fact, MESH can also be seen as an autoencoder with constrained activations and one-shot learn weights. And when we compare it to a tail-biting autoencoder that also acts as a content-addressable memory, we find that MESH shows gradual degradation of information per pattern and can store many more patterns relative to an autoencoder, which shows this catastrophic drop. And we can also see the same thing numerically. So now that we've seen what MESH can accomplish, we will see how MESH actually works. So first we look at the memory scaffold. Memory scaffold stores pre-structured states with no information. And because these states are pre-structured, that's why they don't have any information. And this scaffold is implemented by a two-layer recurrently connected neural network, where the label states represent binary 0-1 states that are k hot and NL dimensional. The weights from the label layers to the hidden layers are random. The hidden layers are defined as random projections of the label layer, and back projections from the hidden layer to the label layer are learned through one-shot associative Hebbian learning. We find that the memory scaffold stores all states as fixed points. Given a critical number of neurons in the hidden layer, memory scaffold is able to stabilize all states on the scaffold up to NL choose k points as fixed points of its dynamics. And more importantly, asymptotically with large NL, this critical number of hidden neurons becomes independent of NL and only scales linearly with k. Further, we also find that memory scaffold has an exponential capacity in the number of label neurons. Assuming a constant density k by NL of stored labels, as we increase the number of label neurons, the number of successfully recovered patterns increases exponentially. So now that we've seen how we can build a memory scaffold, which has an exponential capacity, we are ready to store actual content-laden patterns into this network. So we can store arbitrary patterns into this network by representing them through the feature layer, which is associated with the scaffold through online pseudo-inverse learning, which approximates the offline pseudo-inverse matrices. Now, given a noisy version of a previously stored memory, this network computes a noisy hidden state, which is then used to compute a noisy label state that can be cleaned up through the top k winner-take-all dynamics on the label layer. And this cleaned up label state is then used to reconstruct the cleaned up hidden state, which finally reconstructs the stored memory. We find that in this network, going from features to labels is a perfect map. Labels are recovered perfectly for storage of exponentially many patterns up to the total of NL choose k patterns. However, recovery of features from labels is what leads to a continuum. So only up to NH arbitrary patterns can be recalled from labels, as shown by the green curve in this plot. And beyond NH, this model leads to a continuum of recovered patterns, such that the information per pattern degrades smoothly as we store more patterns into the network. And although these patterns are partially recovered, we find that the partially recovered patterns still continue to lie near the true patterns. So if we examine the feature space, we find that the recovered patterns lie on top of the true patterns for up to the storage of NH patterns. Beyond NH, we have a gradual departure of recovered patterns from true patterns. However, these patterns still continue to lie within the correct Von noise cells. Now, why is the feature layer to label layer a perfect map? In order to understand this, we see that we make an observation that going from features to labels is a computation that is similar to projecting this NPATS dimensional vector, where NPATS is the number of memories stored in the network, onto an NF dimensional plane. And since the number of patterns that we can store in this network is always less than NF, we always recover complete information. However, when going from labels to features, that's not a perfect map, and that's what leads to a continuum. And this happens because this computation is now analogous to projecting this NPATS dimensional vector onto an NH dimensional plane. And since as long as the number of patterns is less than NH, we recover complete information. However, as we increase the number of patterns beyond NH, we start to lose information in those extra dimensions. And that's what leads to partial recovery, leading to a continuum. So to summarize, mesh is a biologically plausible associative memory model without a catastrophic memory cliff. It generates an exponentially large number of fixed points in the memory scaffold, and the heteroassociation then tags arbitrary patterns to these fixed points. We find that mesh leads to a smooth trade-off between the number of memories that can be stored in the network and the richness of those memories.